What's going on, guys? In this video we are going to see how to solve a second order non-homogeneous Cauchy Euler equation. Now first of all we have to know how to identify a Cauchy Euler equation. To identify you have to compare the degree and the coefficient, power of the coefficient, and here we have x square and y, the degree is 2, and then x power 1 degree is 1 and y, and then x power 0. So we have this pattern like this, and after you identify it's a Cauchy Euler equation, to solve Cauchy Euler equation we have to have a complementary solution like yc, and also we have to have a particular solution, because in the final answer to find the general solution this is going to be the equation yc plus yp. So we have to have the complementary solution and also the particular solution. Now to find the complementary solution, what we do is we arrange this equation into a auxiliary equation and find out m values, and that's going to give us the x power whatever the value we have. If we get m values that is distinct real roots, that the pattern of the complementary equation is going to be like this, and if we get same m values the equation is going to look like this, and if we get a complex values the equation is going to complex numbers, the equation is going to be like this. So let's see what we get from here. To find the real roots we have to arrange this one into, to find the real roots, actually roots, we have to arrange this one into auxiliary equation like this. Now first of all we have to know, let's see whether this is a Cauchy Euler equation. You can see this is a degree 2 and then x square, degree 1 x, and degree y and x power 0. Okay, so this is a Cauchy Euler equation. Now first we have to find the m values. To find that we arrange this in the auxiliary equation pattern, and from here you can see that a is equal to 1 here because the coefficient is 1, and this is negative 2, b is equal to negative 2, and then c is equal to 2. And after we find out this one we have to arrange this one into auxiliary equation like this, am times m minus 1, so this is going to be 1 times m minus 1 plus bm, b is negative 2, so this is going to be negative 2 m, and c is 2 plus 2 is equal to 0. And if you multiply this one you will get m square minus m minus 2m plus 2 is equal to 0. From this one we can see that's m square minus 3m plus 2 is equal to 0. Now let's see whether we can factor this one. When we multiply we have to get 2, when we add we have to get negative 3. So minus 2 and minus 1 will work, so we can say m minus 2 m minus 1 is equal to 0. From this one we can see that m is equal to 2 and m is equal to 1. Here we are getting two different values, right? M is equal to 2, m is equal to 1. So this is matching with this one because two distinct real roots, that's this one. So we have to put the equation, the complementary equation is going to be like this. So yc here is going to be c1 x power m1 value, so here this is 2, so c1 square, and then plus c2 and x power m2 x power 1, so that's going to be just x. Okay, so this is our complementary solution. We need this one for the last part because for the general solution we have to add complementary solution and particular solution. Now we have to find particular solution. To find the particular solution we are going to use variation of parameters technique. Now to do the variation of parameters we have to find the Wronskian equation. We have to find this wy1 y2. To find wy1 y2, here we can, from this equation we can find our y1 y2. We take this one as y1, this one is y1 and this is y2. Okay, so y1 is equal to x square, y2 is equal to x. Now we had the previously we had this is our main equation. Okay, now in order to apply variation of parameters you can see that we have to have this pattern y double prime and this pair like this, x function y prime x function y, and that is equal to an x function. So you can that first you can see that first one, when we have y double prime in front of this the coefficient is 1, right? So we have to bring the same thing right here. So in order to do that we have to divide everything by x square. Now let's go ahead and do that. So this is going to be x square y double prime divided by x square minus 2x y prime divided by x square plus 2y divided by x square is equal to 2x cube e power x divided by x square. So if you do that, let's continue this one right here. If you do that, you will get y double prime minus 2y prime over x, and then here we get plus 2y over x square is equal to 2x e power x, 2x e power x. Okay, this is what we have right here. Now after we get this one, let's see what we do. So we have to arrange this one in this, like, to find the particular solution we use this variation parameter equation, but we have y1 y2, g of x is going to be this function 2x e power x. Let's note that one down. G of x is equal to 2x e power x, and we have g of x and we have everything, but we don't have the Wronskian equation. To find Wronskian equation, what we do is we put it in a matrix form, x square and x, because y1 is x square, y2 is x. Okay, I'm taking this one because wy1 y2 is the Wronskian equation. So x square x, and then we put it in a matrix form. So here we put x square x, and we find the derivative of this one, and the derivative of this one is 2x, and the derivative of this one is 1, and you multiply, cross multiply, and do AD minus BC. So AD is x square minus BC is 2x square. AD minus BC, x square minus 2x square, that's going to give you minus x square. Okay, AD minus BC, I mean when we have A, B, C, D, AD is this one minus BC. Okay, so we get this one. So this is our Wronskian equation. Now we can go ahead and plug it in this YP formula, this variation of parameter equation. Now in order to do this, we need a big space. So what I'm going to do is, from here, the important thing here is this one, this complementary equation we need at last. So I'm going to note this one in on top and erase everything else. So yc is equal to c1 x square plus c2x. So this is our complementary equation. Okay, let's put it here and let's erase everything else. Okay, so here I get rid of all of these things, and also we have to know that y1 is x square, y2 is x from this complementary equation. And also we have to know the Wronskian equation. Now let's note everything we needed. So this is one of the information we need, and also we have to need, we know that g of x is 2x, and we found out Wronskian equation w y1 y2 we found out from this equation, that is negative x square, and from this one we know that, so let's erase this one too. We note this one down right here. Okay, and the next thing we need to know y1 and y2, and we know that y1 is our this value and y2 is this value. So y1 is x square and y2 is x. Now let's go ahead and plug it in the variation of parameter equation, that is yp of x is equal to negative y1 is x square integration y2 times g of x. Y2 is x times g of x is 2x e power x, so that's going to be 2x square e power x, and then divided by Wronskian equation, that is negative x square, and then dx plus y2 is this value x, and then integration w1 g of x. W1 is x square times g of x, that's going to be 2x cube e power x divided by Wronskian equation, that's going to be negative x square, and that's it, df dx. Now let's see how we can integrate this one. Before I do that, let's simplify everything. So this is going to be negative negative, that's going to make this one plus. So let's put plus x square, and if we simplify this one, this is going to become just 2 e power x, and also I can move the 2 to the front because 2 is a constant. 2 to the front, x e power x dx, plus here I can move this negative to the front, so this is going to be minus, and here we can cancel this x square and this x cube, so that's going to become just x, and also I can move this to 2 to the front, so this is going to be 2x integration x e power x dx. Okay, and now this integration is easy because e power x, if you integrate e power x, that's going to be just e power x, so this is going to be 2x square e power x minus 2x. Now here we have to do the integration by part, so if I take u as x and v as e power x dx, du is going to be dx, this is dv, dv is equal to e power x dx, therefore v is going to be equal to e power x. Okay, now we have this one, and we know that integration by parts equation is integration u dv is equal to uv minus integration v du, and u times v is going to be x e power x minus integration of v is e power x du is equal to dx, and here if we integrate this one, that's going to be just e power x, so x e power x minus e power x, and that's it. Now let's go ahead and plug everything together. So here we got the previous part until this one. Now we integrated this one right here, and we found out this one. Now we can plug everything together. So what I'm going to do, I'm going to move it to the front a little bit like this, and 2x square integration of this one is just e power x minus 2x multiplied by this one x square, like actually xcx x e power x minus e power x. Now let's multiply and see what we get. Here we can see 2x square e power x minus 2x square e power x, and minus minus plus, so that's going to become 2x e power x, and here you can see that this one and this one cancels each other, so finally we end up with 2x e power x. So that's going to be our particular solution. Yp is equal to 2x e power x. Now we have the particular solution, and here we have the complementary solution. So the general solution for this differential equation is going to be y of x is equal to yp plus yc, and the particular solution we found out that is 2x e power x, plus the complementary solution we found out that is c1x square plus c2x, right? So this is our general solution for this differential equation. Now let's arrange this one in a little better way, like we can put the constant front, so c1x square plus c2x plus 2x e power x, and this is going to be the general solution for this Cauchy Euler equation. I hope this helps. Thanks for watching.